Before we begin this new chapter, let's briefly look back at what we established in Chapter 3, because perturbation theory grows very naturally out of those foundations. In Chapter 3, we begin with Schrödinger's wave equation, which gives us the basic dynamical equation of quantum mechanics. We then introduced dynamical variables and their corresponding quantum mechanical operators, and from there, we studied the eigenvalue problem for a linear Hermitian operator. That discussion was extremely important because it taught us that physical observables are represented by Hermitian operators and that the measurable values of those observables are their eigenvalues. After that, we examined further properties of operators, and then, in the language of linear vector spaces, we reformulated quantum mechanics in a more general and powerful way. In particular, we discussed basis states, operator matrix elements, and the circular equation in matrix form. So by the end of Chapter 3, we had already arrived at a very general framework. Once a basis is chosen, a quantum mechanical problem can be represented as a matrix eigenvalue problem. In principle, solving that matrix equation gives us the allowed energies and the corresponding quantum states. However, that immediately arises a practical question. What do we do when the Hamiltonian of a system is too complicated to solve exactly? That question brings us to this chapter. In many realistic physical systems, the full Hamiltonian cannot be diagonalized analytically, and sometimes even its matrix circular equation is too complicated to solve in closed form. But very often, the system we want to study is not completely unfamiliar. Instead, it differs only slightly from another system whose solutions we already know. In such cases, rather than solving the full problem from scratch, we treat the complicated system as a non-solvable system plus a small correction. That is the essential idea of perturbation theory. So conceptually, perturbation theory is an approximation method built on the operator formalism and eigenvalue theory that we already developed in Chapter 3. We start from an unperturbed Hamiltonian whose eigenvalues and eigenstates are known, and then we add a small extra term, the perturbation term, to describe the weak influence that makes the real system more complicated. Our goal is then to determine how the energies and eigenstates are modified by that small additional term. We now build on stationary states, the normal eigenfunctions, and Hamiltonian eigenvalue problems introduced earlier. This chapter is organized into 4 parts. We will first introduce the general idea of perturbation theory. Then we will study time-independent perturbation theory, where the extra interaction or perturbation does not explicitly vary with time, and we mainly ask how the stationary energies and stationary states are corrected or modified. After that, we will move to time-dependent perturbation theory, where the perturbation changes with time and can induce transitions between quantum states. Finally, we will discuss harmonic perturbation and Fermi's golden rule, which are especially important for transition rates induced by oscillating fields such as electromagnetic radiation. So conceptually, this chapter is about moving from exactly solvable ideal systems to realistic systems subject to weak disturbances. Mathematically, it is about using a known basis of eigenstates to construct approximate energies and approximate wave functions for the slightly modified problem. Physically, it is about asking 2 questions. First, how are the stationary energy levels shifted by a weak disturbance? Second, if the disturbance changes in time, how does it induce transitions from one state to another? Those two questions correspond to the two major branches of perturbation theory that we will study in this chapter. So as we go through the chapter, I would like you to keep one key phrase in mind: small departure from a known system. If the departure is sufficiently small, perturbation theory is often the most efficient and physically transparent approach. Let's now state the formal starting point of perturbation theory. In many practical physical systems, the Schrödinger equation does not admit an exact analytical solution. However, if the Hamiltonian can be separated into two parts, then the problem may become tractable. We write the full Hamiltonian as shown in this equation, where h hat naught or h hat 0 represents the unperturbed stationary Hamiltonian. This is the Hamiltonian of the problem that we already understand. Its eigenfunctions and eigenvalues are assumed to be known. In other words, we know how to solve the unperturbed eigenvalue equation as shown here, and the unperturbed eigenfunctions form an orthonormal set. The unperturbed eigenstates form the basis in which a general state of the unperturbed system can be expanded. So h hat naught is our reference problem, our zeroth order problem, the simpler system from which we begin. Please note that in this chapter, we use superscript 0 to indicate quantities associated with an unperturbed system. The second term, h hat prime of Rnt, is the perturbing Hamiltonian. In general, it is a function of position and time. It represents a small departure from the unperturbed system. The word small is important, and it should be interpreted carefully. It means that the effect of this extra term is weak enough that the exact eigenvalues and eigenfunctions of the full Hamiltonian remain close to those of the unperturbed problem. So the essence of the perturbation theory is this: instead of solving the full complicated Hamiltonian directly, we start from the known eigenstates of the unperturbed Hamiltonian, h hat naught, and then calculate how those known energies and wave functions are modified or corrected by a perturbing Hamiltonian. In other words, perturbation theory is an approximation scheme built on a known basis. As we will soon see, it allows us to obtain corrected energies and states in a systematic, order-by-order manner. We will see that zeroth order means the unperturbed result. First order means the leading correction caused by the perturbation. Second order gives the next correction, and so on. This is an important conceptual point. Perturbation theory does not discard the original exact problem. Rather, it uses the exact solution of the simpler problem as the foundation for approximating the more realistic one. So whenever you see perturbation theory, please ask yourself three questions. What is the unperturbed Hamiltonian? Is it solvable? And in what sense is the perturbation small? If we can answer those three questions clearly, then we are usually in a good position to apply the method. To help you better understand how we go from an unperturbed problem to a perturbed one, here is a useful example: an infinite potential well in the presence of an externally applied static electric field. On the left, we have the unperturbed infinite well, centered symmetrically from z equals minus a over 2 to z equals a over 2. Inside the well, the potential is flat, and outside the well, the potential is infinite. This is a standard exactly solvable problem. Its energy levels are E1 naught, E2 naught, and so on. On the right, an external electric field is applied along the z direction. That field tells the potential energy inside the well, so the flat bottom well becomes a slanted well. Here, when a static electric field is applied in the plus z direction, the potential V of z is tilted downward to the right according to the relationship between the electric field and electric potential as shown in this equation. Since the electric field is the negative gradient of the electric potential, the field must always point in the direction of the steepest decrease in potential. Now the potential due to the externally applied static electric field is given by the line integral of the electric field with respect to z, as shown in this equation. The result is minus capital E sub external times z. Taking the flat bottom infinite well as the zero reference unperturbed system, the change in the electron's static potential energy is then given by the result shown here. Since an electron is negatively charged, we have a minus sign here. Therefore, the potential energy is tilted downward to the left rather than to the right. So relative to the original flat bottom well, the perturbation is the change in the potential energy. The full Hamiltonian is therefore written as shown in this equation. This example shows that although the original infinite well is simple, the tilted well is no longer easy to solve directly. But if the electric field is weak, we do not need to solve the new problem from scratch. We can treat the field term as a perturbation and compute how the original energies and states are modified. Now let's classify perturbation theory into two major cases. The first is time-independent perturbation theory. In this case, the perturbing Hamiltonian has no explicit time dependence, so we may write it as shown. Here I adapt a calligraphic script for the time-dependent Hamiltonian operator and Roman lettering for the time-independent case. Physically, this means the system is modified by a static perturbation. The perturbation changes the stationary energies and stationary eigenfunctions, but it is not itself driving the system in time. The second is time-dependent perturbation theory. In this case, the perturbation explicitly depends on time. Then the Hamiltonian itself changes with time, and the perturbation can induce transitions between different unperturbed states. This is the framework we will later use for processes such as absorption and emission under electromagnetic excitation. Finally, note that for now we consider only the non-degenerate cases, meaning each eigenfunction corresponds to a different eigenvalue. In the non-degenerate case, the formulas are cleaner and the conceptual structure is easier to see. When degeneracy is present in the unperturbed energy spectrum, ordinary non-degenerate perturbation theory, which we will be studying in this chapter, breaks down because the denominators involving energy differences can become problematic, and we must use degenerate perturbation theory instead. In degenerate perturbation theory, the mixing of degenerate states is resolved first before the perturbative correction formulas can be applied. So the message of this slide is, when a weak perturbation is introduced into a system with a non-unperturbed solution, the appropriate treatment of the perturbed system depends on whether the perturbation is static or time-varying. With that conceptual framework in place, we are ready to begin the actual machinery of non-degenerate perturbation theory. We will start with the simpler case, namely time-independent perturbation theory for non-degenerate systems, and derive how the energy and wave function are corrected order by order.